Right, welcome back to session 2, where we're going to do the same problem again, but this time we'll just be using trigonometry to solve the problem. Again, we'll put in the missing information. The aircraft shown below is descending steadily to glide at an angle of theta to the horizontal. There's theta, the engine is cut out, and equilibrium is maintained. That is the important question, because that tells us that all the forces are in balance. And will form a triangle when we join them head to tail of the vectors. Three forces to be in equilibrium, then our leftwards must equal rightwards, our upwards must equal downwards, for all forces being linear. Assuming the above conditions are met, W equals 120 kilonewtons and theta is 20 degrees. Now I like to redraw this part, just taking out all the information that's not required. We really don't need to require the picture of the aeroplane, and we can add in any other information that we want. So first off, we have a force acting down of 120 kilonewtons. We have a force acting at 20 degrees, and we assume it's going in that direction because it shows us it's going in that direction. And then we have a force acting at a right angle here, and that one's L, that one's D. If we take that up, we can then discover that that's 70 degrees, which will make that 20 degrees. So we've got some information. Now we can simply sketch our triangle using 1, 2, 3. So we come down, we know that that's 120. We know we have an angle going off here at 20 degrees there, so that would be 70. And we know L, we don't know where it starts on this line, but we do know where it finishes. So that's going to come down roughly about there. That would form a right angle. If you followed that through, there's our right angle we've got here. And we want to find this angle here, which would represent this angle here. Well, because opposite angles is 20, then that would be 20. A quick check, 20 and 70 is 90 and 90 is 180. So there's our quick check. So now we want to find L and D. Well, if we use the 70 degree as our theta, then L becomes the opposite side, D becomes the adjacent side, and of course the 120 is the hypotenuse of our right angle triangle. So we can solve it simply by using SO, CAR, TOA. So solving L first, we've got the hypotenuse. To solve L, we've got the hypotenuse, we've got theta, and we're looking for the opposite, so we would use the SO section. Sine theta equals opposite over hypotenuse. We're looking for the opposite, so if we rearrange that formula, H sine theta equals opposite. Now we can put our information in. 120 sine 70 will equal our opposite. And I'm just going to put you on pause. So we just reach for our calculator, and our calculator knows bed mass, so we can just put the numbers in as they're written here. 120 times sine 70 equals 112.7. So L is 112.8. Remember to do your rounding. We've got the 6, so that makes it an 8. So that's correct to four significant figures. Now we'll do the same again to find the adjacent. Again, if we're looking for D, we have the hypotenuse, we have theta, and we're looking for the adjacent. Just note, I won't use a number that I've calculated unless I have to, because if I've got that wrong, it will make this wrong. So I always go back to the information that we've been given. So, hypotenuse, theta, adjacent, we'd have to use the cosine, the cos or car. So cosine theta equals adjacent over hypotenuse. If we rearrange that formula, H cos theta equals adjacent. Now we can put our numbers in. 120 cos 70 equals, and go to our calculator, 120 times cos 70 equals, and we've got 41.04. 41.04 kilonewtons. Now, how do we check that? Well, we can use Pythagoras' theorem. Theoretically, 120 squared, our hypotenuse, should equal 112.8 squared plus 41.04 squared. So I'll just hit that, squared plus 112.8 squared equals, square root the answer, and we get 120 with a slight rounding error. So I'm happy that that's correct.